code, or advent of code rather, and we have been prepping somewhat. I added the data for day 7 just to have that done, and just prepped some example code or example input here to have something to work with. Today it seems that it is a slightly different type of problem. Prior to this, it's basically just been nice lists to deal with. But today we have a bag in a bag in a bag problem, I guess. So what it entails is basically that we have a shiny gold bag, and apparently there are some rules that a bag must contain some other bags, and so on. So we have a shiny golden bag, and what we want to know is how many bag colors can we eventually contain at least one shiny bag. So if we have here in this example, we have a shiny gold, and for example a muted yellow contains a shiny gold, 2 shiny gold bags. So the question here, what it kind of boils down to, I guess, is how many bag colors can eventually contain at least one shiny golden bag. So if we look at this as a directed graph, it kind of, I expect it looks something like this. I'm not really good at graph problems in general, but so you have A linking to B and B linking to C, and then we have B also linking to D, and so on. So what the question is, or at least as I am interpreting this, is how many bag colors can eventually contain at least one golden bag. So we have this graph, and let's say for sake of argument that we have D here as our golden bag, and the question then goes, how many different bags can contain this. So since we have a directed graph, the golden bag in itself has some sub bags or bags that itself can contain, but we assume that it's not a cyclic graph because that would mess things up. And so in this case it would be B and A that could contain D, seeing that A must contain B and B must contain D. So I think the first thing we want to do is take this and let's just roll with this to start with. So this is the example that they were giving us. And so what we want to do, can I do this? No. So what we want to do is create our, so the first thing we want to do is basically just create our graph. I'm not really sure how to do this in Reason, or what might be the best way to do it, but I guess I'm gonna try something out. Our first thing is just to parse the inputs. So let us start off with this thing and see where this takes us. So if we look at this, it's basically we have a node is a light red bag. That would be, I would consider that the node, and the bag contains one bright white bag. So that would be an edge leading to from the red bag to the white bag of a weight of 1, and then with a weight of 2 we have an edge leading to a muted yellow bag. Seeing that we only want to look for how many bag colors that eventually contains at least one golden bag, we want to traverse this backwards. So we have to do something with that, but we'll start off with just a parsing, and it doesn't seem that we're interested at the moment, probably in question number 2. We're probably not interested in the weight of the edge, at least for at the moment. So we'll start off with trying to parse this. So, and we'll see where that takes us. So we'll start off with some string operations, I guess. So this we want to turn into a list, and I had some what was it called? String split. There we go. So each line contains one or some node relationship, I guess. So from here we have a list, and now we want to map this into one node and edge pair. So each line we want to map. So let's just call this a line, and so each line here, that would be this thing. So from the start, we kind of want to remove the last char. The dot doesn't really give us too much. So that's one thing. We kind of want to split the thing into two different parts as well. So bags contain, that would be like a keyword defining the edge between, or one or multiple edges between the first node and the two latter nodes. Or two or no nodes in this case. So my basic idea here is to so I think where I'm going with this is, how do I represent this graph in Reason? And I'm not sure. I mean, you could probably do something with an actual link, like type of a linked list or a linked graph or something, but it seems slightly overkill. So what my idea is to have a bag as a map, or a typical regular map with a string and then a list of other nodes here, and then like the node names of string, and then the ints for the weight. So this list, then we could make it so this would be a directed graph in one direction, and then we can have a map that does this in an opposite direction. So what we want to do is actually have the opposite. But let's start off with the regular list. So we have this, and we kind of want to split this into two again. So let's call it pairs or something. And that's the list. Oh, right. Just let us start off by removing that dot that we're not interested in. And then we had string replace, and that's supposed to take a regex, I believe. And we're supposed to replace the dot with something else. And we could probably just log a, and we'll see that this problems already. Oh, there we go. I think it's one too many parentheses. Right, need some dashes in the right direction, I guess. So there we go. So apparently we did not replace the dot. Is there supposed to be like two? What if I replace it with a place of 4 or 2? Does that work? That works. Oh, right, I'm replacing it with a dot. That makes sense. There we go. So now we remove the dot, so that's just easier to work with, I guess. So that's the first portion. And now we want to keep going here and split this into split string, and we want to split this with the delimiter bags contain. And we'll add some spaces on each side, so we just trim the stuff. So that would be nice. So this will probably give us a list of 2. Let node be equal to a list.head and edges maybe. So that will be the tail and then the head again. So if we log these 2, edges, we should get something. Okay, let's add something here too. So there we go. So we have a light red bag, would obviously be the keyword. We probably could remove bags and bag as well. So let's do this up here just to clean things up. No. Yeah, maybe. Okay, so I guess it's always preceded by a space, bag or bags. So I guess we'll do that, and then we'll just add some string replace. All right. And we'll replace bag. Oops. And bag. We'll add a space there. And we'll still split it on contain. And we'll see what that ends up with. So now we have the bag, the edge leading to the bright white bag, and the 2 muted yellow bags. So getting some helpful comments here. It's always nice. So yeah, so now we have the nodes, the edges. So now we're gonna try to parse this again. So the edges we see here are delimited by a dot or a colon or yeah. So this is the delimiter basically. So we want to parse these into actual nodes. So the edges will split, string split in where we have a comma. So now edges would be a list containing 2 1 or more edges, I guess. So now we have the actual list here. We want to parse these again. So now we want to map these. So we want to map this to something that we actually can do something with. So I'm guessing the first portion here is a number. So the weight, weight would be equal to s out dot string split, and we'll split that on just a regular space. The head of this would give us a number, right? Head, and we'll convert that from a string, or we'll get an int of a string. So this would result in the weight, and now we just have the remainder, which would be the tail. And we know that this is actually just there's always two names to the bag, I guess. So this doesn't really work for no content or no others. So I wonder what we should represent that as. So I have let's just remove these here. So this, so let's see here. We have A, which would be the split thingy. Yeah, okay. Let's think about that later. So the next portion would be to assign the name, which would be, I wonder if there's a way, some string functionality to join a list. So let's see for a list, just to have some easier. Do I have a join here? No. Oh well, let's make it ourselves. So S then. Right, we haven't actually split it. So let's split it again, and then we'll take the tail this time, and the tail would then be. We'll have to reduce this. So fold left, and we have the accumulator, and we have the stir, and we'll start off with an empty string. So I guess we'll just add the accumulator. I'm sure there's a better way to actually do this. So we want to concatenate this string. This seems like it's getting more complicated than it should be. But the idea here is basically we'll take the tail, which would be this part, and then we'll just make it back into a string. So I wonder if I should make this, let's see here, string. Do I have something joining? Let's see here. No. Okay. I'm getting some advice here from so probably should switch these around. All right, thank you, Linus. So okay, so what we want to return here is our weight, or our name, and our edge, or our weight rather. So now, yeah, things fail, and that's because here we use our string of int thingy here, that basically converts, or try to convert the first this portion to an int, which doesn't exist where we have no edges. So I guess this could be remedied by simply looking at, so edges that might be, so this will be a list of, or the idea is to have a list of tuples, I guess, something like this, like blue and 1 or something like that. So I guess like no nodes would be an empty list. So what we want to do here is if so if S, yeah, so if S equals no, what was it? No other. So that's our stop word. Then we'll return an empty list. Else we'll return this. This list. Yeah. All right, let's see if this works. No, still something bad. The value S cannot be found. Have I not declared this? Oh. This should be this thingy. There we go. So what we result in is list, and then a 0 value for these two. Okay, so now we still have the first the first char here. So let's deal with that. So we have a string sub. I have to pass this into, yeah, that's the first parameters, I believe. Yep. So we want to take from the first until the last. So that's name or string length. So this is becoming messy. Name, and I guess we should subtract 2 from it, maybe. And we'll see what happens. Yeah, that was 1 too many, so just 1. So now we have trimmed the white spaces off in the front. So now we have our nice edges. So let's break this into something more easily parsable to see what we're doing. Let parse edges. And we'll take a string and we'll just move this whole part here. So what we're interested in is this part. Now we switched the names on this, but so we'll take a string. Oh wait, let's keep it an A. So we'll take the string and we'll parse the edges. The node will end up being the same. The edges now is simply a pipe through parse edges. And we'll see that we get the same result. Yes, nice. So this now should be a tuple. So what we want to do now is create some sort of map structure so we can traverse this, right? And we have in maps are always slightly difficult to work with, or at least that's my experience. So it's somewhat complicated, but I think I created one the other day. So let's copy and paste stuff. Here we go. So let's bring this with us. So what we want to do is create a map, and so the result of this should really be the map, right? What we want to do is as the key we want the node, and on the value we want the list of all the children, or the sub the sub node or the children to the node. So in that order, we can basically traverse the graph by looking at the value and then grabbing that and looking at that one, and then we can recurse over that. So we'll have a string map, smap for short, and t is basically the key for this map. So I think this should be good to go. So what we'll do here, so this takes so this maps all the strings, and now we want to kind of reduce this into, okay, so the next step here, so now we have, so let's return a tuple, node, edges. So this is what we map the string to. So one of these lines get mapped to node and edges. And this we want to reduce. Fold left. Our accumulator, which would be our map in this case, and then we get the pair, maybe. Always hard with naming. We'll do some code here, and here we start off with an empty smap. And that will become our accumulator over here. So now, what we want to do is, so we know this is a directed graph, right? So I wonder, is on the left side, that means on the left side, this can only occur once. Otherwise, we would have we would have multiple relationships, so that would be confusing. So I'm gonna assume that the left side only occurs once. So that means in turn that each node is unique. In our edges, let's see here. So what did these return? So they returned a list, right? So they returned a list of edges, and that's probably what we want to do here. So cmap, smap, add, and we want to add, let's see, what's the syntax for this? So we'll take the key, the element or the value, and then the map of the value to assign. So that would be accumulator passed into add, and we'll add the, okay, so we have to get the key or the node. So that's equal to pair. And here we'll add the node. And here we add the edges. Okay, so this will now fold into a map. So right here, we're supposed to be given a map. So let's call this a graph. And we'll just JS log this to see that things work. Okay. Yeah, so looking at this, we have a bright white with a value dark orange. I'm always kind of confused how this works. But let's try it out. So we're supposed to be able to get muted yellow, for example, and that should return this tuple, or this list of this tuple. So let's see, how do I get things? Is it find? Yeah, I think it is. So smap find muted yellow, and we'll take our graph. So this returns shiny gold 2 and faded blue 9. And muted yellow, shiny 2, shiny goldy, and 9 faded. Yeah. So this gives us our bag. So what we want to do now, so we want to traverse this. So what the quest is really to find, if I have a golden bag, how many other bags could I fit into this? Or rather, how many other possibilities of bag colors do we have that a golden bag would end up in? So what we do have now is a great position to ask, if I have a muted yellow bag, would that contain another bag of a sort? We could just iterate through these tuples and end up with a recursively run through the graph and find, like, yeah, we contain some particular color. But in this case, we want to kind of redirect the graph, or reverse the flow of the graph rather. So I think this might be just an easy way to start off with. So let reverse be equal to graph. And now we want to, yeah, right, so we want to iterate through the graph again. I wonder if I can just add this when I'm already doing the things. So what I want to do is basically, for each node of the edge, we want to add something to the, it becomes, nicer to do this in 2 steps maybe. Okay. So here, map. What does this do? For all fold. So we kind of want to iterate through these as pairs and then fold over them. And we have iterate. I would like to have this converted into a list. Okay, so what does fold do? So it takes a map of A. You get the key, you get the A, and you get B, which would be the accumulator in this time. Yeah, so maybe that would work. Let's just copy this definition. All right. So we have our S map, and we want to map this. I'm not really sure what I'm doing here, but I get the key, I'll get the val. Okay, let's call that V. And I get the accumulator, and here we're supposed to return something, and seeing that we want to, and here we want to pass in T of A, so that would be our graph, right? Graph, and here we will smap.empty, because it's an S map that we want to get back, but in the opposite direction. So okay, So the key should go into the list of each thing that contains in this value. So this value will be a list of edges. So for our accumulator, for each value that's in our list, we want to add the key to the list if it exists. Not really used to thinking in terms of these ways. So okay, we know V is a list, and V is a list, and we want to reduce that to a map, right? Default left. Yeah, and that's what we want to return. So we have our accumulator, or like 2, I guess, and we'll have our, so we have our node or edges. So we'll get our edge rather. Okay, and from here we want to pass in our accumulator, our real accumulator, that is. Seeing that things are immutable. Okay, so now I have an edge, and to that edge I want to add name, weight. Was that how I defined it up here? Yeah, name and weight. So name, weight is equal to edge. So that will give us our name and our weight. And from here, we want to find, what does find return if it doesn't exist? Erase is not found. That's not too pleasant. So we have our accumulator 2, and that's the one we want to update. So what we want to do is let's call it now for now. smap find, and what we want to find is our we want to find our name for the accumulator 2. So this would return a list as it is now. Okay, so we have to do something like this. If smap, is it mem? Mem, all right. So it mem looks up if the map contains the key name. So we want to reverse this, right? So if it contains this, else. So if it contains the name, we want to do something, and in that case we want to find the key from the accumulator, and that will return the list. Otherwise we'll just add or return an empty list. So if the key exists in the map, we've iterated through it, we passed it once or twice, so now we have what the current state of things are. So now we want to create a new list. So let res equal to now now passed into this, and this would be the list of key. I'm kind of losing the weights here, but I think that's okay for now. So what we do is we take now, which is an empty list or a list, seeing that we passed it before, and to that we append the list of the key that we're at right now. So I think this will reverse things. And now we have the list, and the only thing left is to smap.append or add. Wait, what does add? Does it overwrite? I think it must. The previous binding disappears, yeah. So add, and here we want to add a key, which in this case is the name. Was it the key, the element, and the list? So this would be res, and we're working on Act 2. Okay, so this should now produce the reverse list. So let's just see if things compile. No, it doesn't. This function has the type A to B. Smap of A. It only accepts 2 arguments. Here it's called with more. Ah, right. We obviously have to pass in the accumulator into the map we're checking. Ooh. So now we're back at the rev. Okay, so it contains type variables that can't be generalized, so we have to do that for it, I guess. So the map here would be a string. And this would be a string and a list of string. Does that make it happy? Okay, so now we're looking at the fold left here. So we have the accumulator, which is which we use. People are talking to me. Okay, incompatible parts. Somewhere wanted. Here it has type smap key. V. So we want to return a list of strings. Why is it? Someone sees my error. Please help me out. So this is my, what is it whining about? So it's So the edge here should be each element. Oh, right. So this shouldn't be a... So what happens if we just log stuff? Let's return the accumulator. Does this work? No, still upset to something. Okay, so it's still upset about the weak inference here. So is it the key? Okay. So fold takes the key, it takes A, which is the value. So, and what we added here was the edges. Getting stuck. Feeling that this kind of becomes a boring video. Okay, so the graph, we split up things. Parse edges. So edges in this. And we'll grab node and edges from the pairs that we reduce over. And we'll add the node, which is a string, and the edges. And the edges is a list, an empty list, or split yada yada yada, and we map this to so edges should really be a list of this string and weight. So the key should be a string, and this should be a list of string and ints, a tuple of left strings and int. Incompatible type, graph, want the T of. So does this work, just switching it out? Have I misread the... So this can't work. Yeah, today's puzzle was much harder, especially in a new language and everything. But it seems that no, this feels... So I mean, graph is... What is graph? Graph is the same as empty. And empty is this thing here. I'm pretty sure. So can I just do this? No. Graph has type list. Can't really recall how these comparators work. Wanted. Why would it want to? So to the smap we add. It's always like when you're in a new language, you can't really recall. So we have the key and the value, and we'll have the map of the value, and that returns a map of that value. So here we have that value. So I feel this should be this thing. Oops. But why does it want a T of string? I don't understand. Oh wait, I'm using map. I was supposed to use fold. That's why. That makes more sense. Alright, so what? Why hasn't it been using map? Gosh darn. So this was obviously the things I was trying to use. So we take the key, we take the value, and we'll take B, which is what we want to return. So this would be the accumulator then. And then we'll take the graph and we'll take this map empty. So I have one parentheses too many here. Yeah, so this is. You just remove this portion. Does it figure things out? Yay, at last. Something happens. Okay, so let's try to make the upper portion work again. We obviously used the wrong function. So this is supposed to be a fold, and this is supposed to be the key, this is supposed to be yada yada. We don't really need to know about it. And here we're supposed to take the graph that we want to map over, and we want to return an smap empty. So to here we'll just add a list of strings. Okay, so does this work now? Yay! It produces something. So it's kind of unclear whether this is correct or not. It's all kind of JS, but we'll go from here. We'll hope it's correct. So now this should give us like a reversed graph, or at least so I think. We hope. And the quest now was to how many bag colors can you eventually contain at least one shiny bag? So we want to go from, so the bright white bag, where did we have the bright whites? A bright white which can hold a bag directly, a muted yellow bag which can hold a shiny gold bag, plus some other bags. A dark orange bag which can hold a bright white bag, and a muted yellow bag either can hold a shiny gold bag. A red bag which can hold a bright white, and a muted yellow which either can hold a bright. So this then turns into, so the number in this camp of bag colors eventually contains at least one shiny bag is 4. Are they making up new examples here, or is this actually the right? Do they have dark orange as well? Yeah, muted yellow, bright white. Yeah. Okay, so we should end up with 4 from our test data. So now what we want to do is we have our reverse graph. So from here we want to find, and what was it? We wanted to find our shiny Goldie. Find. And we're passing in this thing. And just log this. So this contains a list with muted yellow, bright white, and so on. So this list we should recurse over, right? And we should recurse over it to find. So each of these bags that this contains obviously is something that we want to find. So let's just call it something. So this takes a node. So this takes a node and returns a list, right? So we have this, and we want to pass this into get list. So this node then contains, so this is a list of other nodes. So to this, and if we look at this, it was just a list that didn't really contain much. But for each of these, we want to append. So we have a node. Yeah, so list. Okay, let's do it the other way around. No, okay, so let's make this function recursive. So if list is empty, n list length. So if this list is empty, we'll just return a list. If it's not empty, else, we'll return so we want to, okay, I'm gonna, so from here we want to look up the new bag, or the, so we want to, yeah, so we want to reduce this, maybe, is it? Okay, so here, so we want to, for each list, so n is definitely what we want, and we, from here we want to append something. So prior to appending this, we want to recurse down. So each of these elements we want to map. And we'll map this with getList. So this will return an empty list if this has nothing else, and then it will return something else. So before we can append this, we have to flatten this. Do we have a flatten thingy? Let's see here, list. So we have a flatten, so that works great, hopefully. Okay. So this now should recurse over this. So first we get our initial point, we send that initial point, which is a list of items, into this one. And this one, if the list is of length 0, it returns an empty list, which is what we want. That's our breaking point. If we can't, no. All right, so yeah, so this just sends get list into this, so this doesn't work obviously. So we have the color. And from here, we want to do some of this if magic again. smap mem. So we have the color and we have the reverse tree. So if we have the reverse tree, then we do this. Otherwise, we'll just return an empty list. So now we know we have something here to look for. So we'll do we're looking at this again. This doesn't turn out to be too pretty, but you know, let's clean up things afterwards so we get it working. Okay, so we want to find our shiny gold, or our color, and this we do pipe into get list. Okay, lot of, oh no. Okay, so that's so here we obviously wanted a bool, which is if this is 0. So flatten, we have to pipe that into append. Alright, doesn't use edge. Let's get rid of that, or wait. Okay, so now we'll have a number, hopefully. Right, so now we have a obviously we have a list here. So now we can list.sort unique, and I think sort unique is sort. So we just want the distinct number of colors, not if they occur more than once. So we just have to pass in a comparator. So I think we have the pervasive comparator, which is just a generic comparator. Oh no. Oh. Alright, so we have our sorted and unique, and now we just need to list.length. So that's 4, and that's actually the answer we were looking for in our test example, seeing that we haven't really piped in the real data yet. So we have string here. Where do we start off with string here? So data.string is our real data, which is over here. And we'll see that there's all kind of different bags. So we get 238 different ones. So let's see if this works out. No, what was it? 238. Yay! A gold star. This took way longer than I thought it would. A lot of an hour. Good of our 3 viewers. It's always nice to have you wait with me. So there's a part 2. Not sure if I'm gonna be able to finish this, but let's give it a try and see how complicated it might seem. It's getting pretty expensive to fly these days because of ticket prices, but because of the ridiculous number of bags you need to buy. Yeah, that would be an issue. Consider again the shiny golden bag and the rules from the above example. Contains 0 bags, dotted black, contains 0 bags, dotted plum, elephant bags, blah blah blah. A single shiny bag must contain 1 dark olive bag and the 7 bags within it, plus the vibrant plum, and there are each of those. So that's 32 bags. Of course, the actual rule have a small change of going several levels deep. That is, example, be sure to count all the bags even if the nested becomes topologically impractical. Of course, the actual rule have small change of going several deeper than this example. Oh, okay. Yeah, so they just want to. So in this case, it's actually the edges that we do want to count, and we're going. So in this example they've described here, the golden shiny golden bag must contain 126 different bags. So actually, this might not be too complicated to solve from where we are. So here we did the groundwork of the graph, which is directed in the way we're going now. So prior to this was how many different bags can we put our golden bag into, and now we're asking how many bags do we have to fit into our golden bag. So that's pretty much the same type of recursive function, but using the other map, I would assume. So if we take our graph, and we'll start off from there. So first of all, we want to, just as we did over here, we want to start off by finding our golden shiny bag. But now all the edges points in the direction that we want to travel. So if we num of bags is equal to, so we'll take a list, and from here we want this to return, we're gonna recursive this, so we want this to return our number of bags that this bag has to fit into. So the question is here as well. Okay, so yeah. Dark red bag must contain. Yeah, so 1, 2, 3, 4, 5, 6. Yeah, so this kind of grows exponentially, I guess. Dark red must contain orange, but okay. Yes. So what we have here. So okay, so this one, golden shiny, it contains Okay, so this contains a list. For each element of the list, so we want to add the list together. So that's a fold, I assume. Fold left, we get accumulator, which is the number that we're looking for. And we get our color. And from here, we know that we start off by 0. We don't need any bags. So I'm wondering if I should count the... Wait, where did it go? So I'm just curious, like, how many individual bags are required inside your single chunk? Okay. Yeah, I was just curious if I need to count our shiny golden bag or not. And since I'm not supposed to count that one, this works nicely. Okay, so each of these. So now we're working with just one. So the name. Let name. Weight. Is equal to C, so this is edge. Okay, so we'll get the name and the weight from the edge, right? So what we want to return is the weight times, so I mean, if we have, so the weight of this edge times whatever number bags these are. So here I assume we want to do number of bags again, but with this thingy. So the weight times the number of bags that must contain. Oh, right, we have to supply the actual name here. So that would traverse that edge to the next node. So the question here becomes, do we... So here, I wonder what happened with our empty. So okay, let's get this number, I guess. Number of bags. JS log do. So that's 0. Oh, right, we have to add the accumulator, obviously. No, that still becomes 0. Wait, so this, what? So this returns an integer. Perhaps if I turn this into 1. So that becomes a big number. Why would this matter? Okay, so for each... So what is the base case here? I feel if the list of L is equal to 0, so that's an empty bag, right? So that would mean we return 1, else we would return this stuff. So that gives us a number. Question is that right? So the idea is we traverse, so that kind of boils down to whatever it was we did up here. Where did we... Oh, right here, parse. So if it was no other bag, we still want to count that one. Or do we? Maybe. Okay. Let's try this out. Nothing to lose. I have a 30%. I'm giving myself a 25% chance of being correct. Yeah. Okay, so the answer was too low. So we need a bigger number. So we have our directed graph. We have our number of bags. So this gives us a list. So what happens if we change this to 0? So that one, so the last bag doesn't contain another bag. But I think this will leave us off with 0, but we have to count. So we are at, so when we're looking at this, we are at the number. So we are at a bag when we're in this fold session, right? So we have to count that bag we're currently at. So that would be, would that entail just adding 1 here? I'm not sure. So we have to add, I mean, so we, yeah. But okay, so let's reason about this. So the first bag we're not supposed to buy, shiny gold. So say that contains 2 bags, or just 1 bag for that matter. So we send that single bag into here. We fold over that edge, or that bag. And what we do is, to the accumulator, whatever that might be, we multiply the number of bags that's in that bag. Yeah. So I think this feels correctly. Anyway. So let's, I think, so it's the current bag plus the number, the weight of whatever that one contains, plus the accumulator, whatever we're adding on added so far. So that gives us 26,000. Now, was that more? What did the... You're not the right answer. Your answer is too low. Yeah. Seems like I'm just guessing here. What happened if I... So that obviously gives us a larger number. I kind of want to figure this out. So in the base case that we don't have any bags, we want to count ourselves. So that's 1 we return. We have no sub bags, and that would be the case of dotted black bag. Because if we look up dotted black bag, it would have an empty list. And that's what we would send into it here. So dotted black bag, we'll send that into, so that will return 1. We get back Maybe we should just try the example they had. So this was the cool. Just place that one, and we'll change. Where did we have the string here? So this was supposed to give us, for shiny gold bag. Shiny gold bag is what we're looking for, and this was supposed to give us 126. And what does this? Oh, not found. What is not found? Didn't we? 126. So this one works. Why didn't this one? So why didn't that one work? Where does it fail? '87. Ugh. Shiny gold, isn't that what we got up here? Shiny gold bag, yeah. Okay. All right, so we're kind of close here now. So we wanted 126. So what would that be? Is it somewhere difference? Quite large numbers when you get into it. So would this be if I send the accumulator? No. So we somehow just need to subtract one here. So I mean, this obviously would, no? Oh. So this obviously would render us, so this would be kind of removing the first bag. But I'm not sure. And what did it, the first, what did this give us? So in that case, that will give us 32 bags. Do we get 32 bags? So we get 32 bags. Okay. So somehow this seems to be what we're looking for. So data string. So what does this give us? So this gives us says this number. Let's see if it is correct. Yay, a gold star. That was quite a long session, an hour 24 minutes, I guess. So I'm not sure. I'm gonna probably end the stream here if no one has any questions, any one of my 2 viewers. Otherwise, I guess I'll end it here, clean up some code, and push it to the Git repository. Yeah. So that's basically it. If someone wants to find me on GitHub. You can find me at, let's see here, yeah. So you find our GitHub. You want to scroll down. Oh, okay. See the solution. See why it works. I'm slightly confused myself about why this would work. In general. I wonder if I could do... Could I do this? I'm just trying things around here. Figuring out how reason works. 1. How about if I do this? So now I'm trying to currying the functions. No, it's still upset. Oh, I just get a extra parentheses. Yeah, so that turns out the same. So here I'll so this was a fun way to add or subtract a number, I guess. I wonder if it works the other way around. I think not. Maybe it does. Yeah, no. I feel this... This is kind of strange, because usually the pipe means that you pipe in the last argument of the function. Which is correct in this sense, I guess. Yeah, no, it actually does work. Wait, no. Oh well. Oh well. Yeah. All confusing. I like the first annotation. It was as confusing as functional programming can be sometimes. But this means a function that subtracts 1. Yeah. So I think, yeah, I'm pretty happy that we actually solved both problems. I think it was much of the work that we did put into the in the beginning with actually mapping up the entire graph with the weights on the nodes that led to this. But I'll probably clean this up so the version that ends up in the repository will probably be slightly different, just for my own peace of mind, I guess. All right, so we'll end the stream here, and nice for the guys who stuck up with me. Bye now.